Okay, we're recording. Check, check. Can you hear me? Can you see me?
Confirmed.
Okay, today's going to be a mind bender for us. Last week, we learned how to work with binary numbers using bit shift instead of the usual place value method. Now, for many of you, that already felt like turning the entire number system sideways. And if that's not enough of a stretch, today we're going to go even deeper. Today, we're going to take a close look at the int data type. Ordinary integer, you've been using this since your very first program, and we're going to see that the int data type doesn't behave the same way that we learned about binaries when we were in the math class. But before we get there, let's do a warm up, a quick review of number line systems we've studied so far. Um, Robert, start us off. What is a number system that we've already learned about?
We previously learned about gray codes. This is where the binary numbers are arranged so they are not in numerical order. For example, 0, 1, 3, 2, 6, 7, 5, 4. When written in binary, each consecutive number differs by only 1 bit.
Yeah, good. That's the key property. Only one bit changes at a time. Now, in ordinary binary, like we learned in math class, if we go from like the number 3 to the number 4, 3 of the bits will change. The 4's place changes, the 2's place change, and the 1's place change. In gray codes, they're arranged so that only one bit changes in between consecutive numbers. So, Robert, what's the computing use case for gray codes?
They are used in systems where changing many bits at once can cause errors. Examples include rotary encoders, digital sensors, and telecommunications.
Yeah, exactly. The more bits that change in between steps, the greater chance of an error. So we arrange the numbers so that if two values differ by only one, then only one bit changes between them. Um, so, all right, who's next? Poppy. Poppy, what's one of the number lines that we studied?
We studied the fairy sequence. It's a number line made of fractions, but the spacing between the fractions doesn't match their numerical value. For example, in the sequence 0, 1/3, 1/2, 2/3, 1, the fraction 1/3 has a value of 0.333, but it sits only 1/4 of the way along the sequence.
Good. Yeah, that's the key idea. The value of a number and its position on the number line aren't the same thing. In the fairy sequence, sometimes the numbers are squeezed closer together or they're stretched further apart, depending on the denominator of the fraction. Now, in computing, why would we use this in computing?
It's used in robotics. Like if we took 5/6 and 7/8, the real average would be 41/48. And that's just too complicated to build into a robotic system.
Yeah, exactly. In computing, and especially in robotics, we often need simple, stable ratios. Motors, gears, timing systems, these all work best when the fractions are small. Fairy sequence gives us a structured way to find these small fractions that they're close enough to the fraction that we actually want. All right, next up, Noah. Noah, just try your best. What is a number system that we've previously learned? Oh, Z, the Z order. Yeah, it's called Morton order. Instead of if we have numbers printed like we read, it goes across, gets to the line break, and then down to the beginning again. Um, Instead of doing it that way, we have it in a zigzag pattern where the big groups start in that zigzag. And then within each one of those, we have a zigzag here and a zigzag here, zigzag here, and a zigzag here. So what's the use case? Oh, your camera. Yeah, that's a good example. In some computer graphic systems, two pixels that are next to each other in memory can be very far apart. Like the printing system. If you go all the way to the end and do a line break, it comes down to the next line. Now, these two pixels are very far apart in the image, but they would be close in memory. So Morton order helps to fix that by making sure that pixels that are close together in memory are also close together in the image. Doug, how about you take a turn? What's a number system that we've learned?
Yeah, we did the vertical number line. It's the one where the numbers go up and down instead of left and right. And the important part is it helps us see that a number line doesn't always have to be that shape.
Yeah, right. Remember our example of walking up flights of steps. Positive is walking up, not to the right. And negative is walking down, not to the left. So what's the computer use case?
It helps us tell the difference between data and the doctors, surgeons. I can't remember the word, but it's the thing that does stuff.
It's operators, Doug. The word you're looking for is operators. And yeah, that's the idea. Think of it like this. You're on the second floor and you walk up 3 flights. That makes sense. You start with a location and you do an operation. If I walk up 2 flights of steps and then walk up 3 flights of steps, that also makes sense. It's an operation added to another operation. But second floor plus third floor, that's nonsense. You can't be in 2 locations. You can only add location and operator, or add operator and operator. All right, that brings us to the last warm-up. Alan, you're up.
We did the clock math one, modular arithmetic. 11 o'clock plus 15 hours is not 26 o'clock. Two numbers can be placed on exactly the same place around a circle. It's basically the number line version of a looped playlist.
Yeah, good. Exactly. And the use case in computing?
Well, there is a new operator when we write computer code. We have plus, minus, times, divide, and now the percent sign. It means the remainder when you divide. For example, on a clock, if you have 27 o'clock and divide by 24, the remainder is 3, so 3 o'clock. You also told us that it appears in cybersecurity, but we are not at the cybersecurity unit yet.
Right. We'll go deeper into modular arithmetic when we talk about encryption. For today, I just want everyone comfortable with the module operator, and we're throwing it in with the other operators of add, subtract, multiply, and divide. Now we have a 5th operator. So today, I'm going to take that idea of modular arithmetic, and I'm going to make a small change to it, and we'll build to something called a Riemann circle. Let me show you how this works. I will change to a whiteboard here. Okay, this is our ordinary number line, the one you've been using all the way back in math class. This is the Riemann circle. The number line stays straight, but the circle sits above it. And we're going to use this top point as our anchor. We're going to change the numbers from the number line and put them onto the circle. And the place on the circle, we draw a straight line from the top point down to the number. And wherever that crosses the circle, that's where the number goes on the circle. So as an example, let's do 3. 3 on the number line is here. We'll draw a line from the anchor point to the number. Now, where that line crosses the circle, which is here, that is where we're going to place the 3 on the circle. Let's do another one, -7. So -7 on the number line is here. We'll make a line from the anchor point to the number line. And wherever that line crosses the circle, that is where we place the -7 on the circle. So -7 would be this place on the circle. There. Okay?
Oh, I get it. This is the same as the modulo circle.
It's almost, but both use the circle shape, but the spacing is completely different. Let me show you. One way to see the difference is to go in the other direction. If we know a point on the circle, where does that land on the number line? So on the circle, this point will match down to the 3. And on the circle, this point on the circle maps to the 7. The question comes up, let's clear this. Okay, what happens if the point on the circle is at the very top? There. Okay, let's do a couple of examples. Let's do this line. Does this line go through our anchor point and also go through the circle crossing? Yes, of course it does. This line, does it go through the anchor point and the crossing point? Also yes. This line, does it go through the anchor point and the crossing point? Yes, it does. This line, does it go through the anchor point and go through the crossing point? Yes. In fact, every line from every number passes through the top of the circle at this point. So in a way, if we put the circle point at the very top, it becomes every number all at the same time.
OMG.
Yeah, it gets worse. Think about how we connect how the connecting line moves. At 0, here, the line is straight up and down. I'm going to move this crossing point, the place where that line crosses the circle. When that moves, watch what happens to the line. I'm going to go here. It goes up and up and up and up. And now the circle point and the anchor point are at the same place. When that happened, the line becomes completely parallel with the number line. And we learned that parallel lines they never meet. So in this way, the top of the point, whenever you put the circle point directly on top of the anchor point, it becomes no number on the number line. So let that sink in. The top of the circle is every number at the same time and also no number.
Wait, what? That can't be right. How can it be both?
Okay, it's not right. That's not what actually happens in real computing. And it's not actually what happens on a Riemann circle. I'm just showing you a simplified version to get across the idea that strange things happen when we get close to the edges of the number line. Usually we can't see this because those strange things are out there on the edge. But when we wrap this, we can see specifically this point right here. That is where all the strangeness happens. Okay, so now we have two tools. First, that the number line doesn't always have to be a straight line. And second, we have a basic understanding of a Riemann surface. It's a circle connected to a line. We're going to use those two ideas together to continue our understanding of binary numbers. I have some computer code set up. Let me share my screen to here. Okay, let's remember what this code does. Where it says double the current value. Doubling or multiplying by 2, computers don't have that. They just have and, or, and not. So we have to bit shift. Bit shift is basically the same thing as multiplying by 2. And for the second one, add 1 to the bit if it's 1. Again, computers don't have the add operator. The only operators they have are add or not. So what we'll have to do, we use the or operator, we use the OR assignment operator if it's equal to 0 in order to OR the two bits together. So in this example, we have this number, 00101010. I want you to convert this from binary to decimal. So who can I call?
Sure, we like this one.
Hmm?
Double and add 0 is still 0. Double and add 0 is still 0. Double and add 1 is 1. Double and add 0 is 2. Double and add 1 is 5. Double and add 0 is 10. Double and add 1 is 21. Double and add 0 is 42.
Okay, so 42, let's run the program, see if you're correct. Compiling. 42, that's correct. So let's go to here. This one, the number 00100101. Need you to convert that from binary to decimal. Doug, why don't you take a turn?
Right. So, the 1's place is 1, the 2's place is 0,
No,
the 4's place is...
Stop.
What?
Doug, you're using the placeholder method. The placeholder method is what we learned in math class. Computers don't use math. We need to do it the computer way. I want you to do this using the double and add method that we learned last week, okay? Start over. Okay?
Right, sorry. Okay, starting over. Double and add 0 is 0. Double again and add 0 is still 0. Double and add 1 is 1. Double and add 0 is 2. Double and add 0 is 4. Double and add 1 is 9. Double and add 0 is 18. Double and add 1 is, 37.
Okay, let's run the program, see if you're correct. Compiling. 37, that's the correct answer. I can tell you've been practicing, so keep up the good work. Let's switch to this one. Okay. So for this number, need you to convert this from decimal to binary. So Poppy, why don't you take a turn?
So 0, 1, 2, 4, 8, 17, 34, 69. Nice.
Okay, let's run the program, see if you got it right. Compiling. 69, nice. So we'll do one more here. This number, okay? Need you to convert this number into decimal. Let's have Robert do this one.
First bit total is 1. Second bit total is 3. Third bit total is 6. Fourth bit total is 12. Fifth bit total is 25. Sixth bit total is 50. Seventh bit total is 100. Final total is 201.
Okay, 201. Let's run the program, see if you're correct. Compiling. -55.
That does not match my calculation.
Yeah, the computer printed the wrong answer. I think the code has a bug.
Is there an off by 1 error happening? Should it be from 1 to 8 instead of from 0 to 8?
Oh, no. There's no off by 1 error. Remember, you count from the start of the index. So that way you're counting the gaps, not the places. This is the correct way to avoid off by 1 errors.
Okay, but why isn't there an else 0 in the code? Like, if the bit isn't a 1, shouldn't we check if it's a 0?
No, we don't need to check. But first of all, binary only has 1s and 0s. So if we've checked 1, we know that the other option has to be 0. But more importantly, whenever we bit shift and move all of the bits one space to the left, the new bit that gets pushed in is always going to be a 0. But if it helps you, we can add that in. Let me change the code here. Else, I'll copy that and paste it there, and then change that so that it's a 0. Okay, I think this is the code that you were looking for. So if it's equal to 1, we OR in a 1. Otherwise, if it's equal to 0, we will OR operator in the 0. Let's run this. Okay. Compiling. Still negative 55.
It's still wrong.
No, Doug. It's still right. Negative 55 is the correct answer. It's the textbooks that's wrong. Let's go back to the number line and hopefully this will make sense. Stop screen share and pull up a whiteboard here. Okay, so this is the Riemann surface that we've just learned. First, let's make 2 changes to it. We'll move the number line to the top. Okay, and second, we'll swap left and right. Here. This is the number line that computers use. We'll make a line from the 0 point to the top of the circle. Here. Okay. And wherever that crosses, that's where the number is. Okay. So here, the -7 would be placed there on the number line. If we have the 3, go from the 0 to the 3, wherever it hits the number line, that's where we're going to place the 3. That way. Okay. Now, there's no name for this, but let's just call this the int data type. 0 is all the way over here on the left and the right. Then we go 1 and start counting up. And that crazy point where everything is strange, that's now in the middle of the number line. It's still the top of the circle, but that place where all logic breaks down is the middle of the number line instead of the edges of the number line. I have another animation set up in case this one isn't clear enough for you. Okay, here is the number line that we learned in math class. 0 is in the middle, and those weird things happen all the way out on the left and the right. The int data type uses this number line. There. Now the 0 point is all the way out on the left and the right. And that crazy place where all of the logic breaks down, that's in the middle of the number line. The positive numbers are on the left, the negative numbers are on the right. So let's take that number that Robert did of 210. The middle point on this number line, it's 127 and -128. That is where it crosses over. So the number 210, that is bigger than the 127. So it keeps on going up. 125, 126, 127. The next number after that is -128. And then we go -127, -126, and on down. That 210, it is crossed over that middle point, and we're now in the negative number territory. Now, the book will teach you starting with the math number line. And you say it gets up to 127 and it wraps around. Or it gets up to 127 and it falls off the edge. It does no such thing. It's just that in the version of the number line used by computers, the next number after 127 is 128.
Oh, we think we got it. In the mathematical number line, we place negative numbers on the left because we're thinking in terms of value. But the computer isn't arranging numbers by value. It's arranging them by bit pattern. We need 0 to be on the far left because a byte of nothing but zeros has to be the decimal value of 0. So instead of 0 being in the middle, we flip-flop the positive and negative.
Yeah, thanks, Alan. That's it exactly. The number line shows values. That is math class. I don't want you doing math. We're in the computing class. I want you doing computing. In computing, negative numbers are on the right. Nothing wraps around, nothing goes off of the edge, nothing jumps. That's just the pattern that the bits are put in. Now, this is called overflow error. And when we use the word error, we think there's some kind of mistake. And the first thing that we would want to do is go and repair the code and fix the bug in the code. There is no bug. That's not what's happening. We can't fix the bug because negative 128 actually is the number after 127.
Let me see if I get it. Is this like the gray code system we used? We still have all the same numbers, but we just pick them up and shuffle them into new places. The order changes so it works inside the computer.
Yeah, awesome thinking. It is like the gray codes. The numbers are the same, but the left to right order is rearranged. It's like shuffling a pack of cards. It's all the same cards. You just pick them up and arrange them in a different place. Now, next week, we're going to go into why this is the case and why computers were set up this way. And, we'll work more on 2's complement, and we'll actually work through that example of the number 201 and why that's actually negative 55. Think that's it for today. We're over on time again. Sorry about that. So remember, the challenge problem is still in effect. I've only received 3 answers so far. Robert has come the closest. Challenge problem. When you have 2 random numbers, we will roll a die 2 times for a number between 1 and 6 and store those in 2 variables. Now, how can we find the bigger value, but without using an if statement? That's the challenge. I'm going to keep this challenge open until I finally get a student that gets the correct answer. But that is it for today. Tomorrow, 2's complement and more work on actually implementing this idea of the number line. The new number line that we learned, the int-based number line, the negative numbers are on the right. That's it for today. Thank you so much. Bye-bye.
Bye.
Thanks.
Stay
All right,
amazing.
see ya.
Ending